Hello, my name is Jesse Singh. I'm a doctoral student at the University of Oxford, and today I'll be presenting on atom probe tomography of conventionally and flash-sintered yttrium stabilized zirconia. Yttrium stabilized zirconia, or YSZ, is a very common engineering ceramic, and as such, there exists a strong interest in more efficient yttrium stabilized zirconia sintering. One potential method for increased sintering efficiency is flash sintering. Flash sintering occurs at a critical combination of electric field and temperature. In practice, a specimen is placed in a furnace, heated to a temperature much lower than that required for conventional sintering, and an electrical current is applied across the specimen length. Flash sintering then occurs in a matter of seconds as opposed to a matter of hours when using conventional sintering. Because flash sintering occurs on such a small time scale, there also exists a possibility for fine microstructural control when using flash sintering. Although flash sintering shows plenty of promise when applied to YSZ, questions still remain regarding the fundamental mechanism causing such a rapid sintering rate. In order to answer these questions, high-resolution chemical characterization of flash-sintered and conventionally sintered YSZ is needed, and atom probe tomography is an attractive technique for doing so. YSZ specimens for APT analysis were sintered using commercially available Tosho powders. Pre-sintering powder processing includes ultrasonic agitation to break up agglomerates, slip casting into a suitable geometry, and cold isostatic pressing before being placed into a furnace for sintering. 4 different types of specimens were studied. Conventionally sintered specimens were analyzed as a baseline. 2 specimens came from opposing sides of the same green body specimen, one from the anode and one from the cathode. Finally, a 4th specimen subjected to a higher current for a longer timescale was sectioned, and the cathode was analyzed to study the effect of a stronger electrochemically reducing environment on microstructural chemistry. Standard fib lift-out techniques were used to create samples suitable for APT analysis, and transmission Kikuchi diffraction was employed to target and characterize features such as grain boundaries and triple points. Furthermore, a parameter sweep of laser energy values was conducted in order to optimize analysis conditions to achieve chemical compositions consistent with powder chemistry reported by the manufacturer. Preliminary grain boundary analysis has demonstrated significant chemical anisotropy at grain boundaries, both between different types of specimens and between different grain boundaries of the same specimen. Shown in this slide are 2 grain boundaries with significantly different chemical segregation behavior, coming from the same lift-out bar. The grain boundary on the left demonstrates significant yttrium segregation, no aluminium segregation, and 3 silicon clusters lying within the thickness of the boundary. The grain boundary on the right demonstrates significant segregation of yttrium, aluminium, and silicon. Although there is a variety of grain boundary types based upon segregation behavior between all the specimens studied, there seems to be no consistent difference between grain boundary segregation and type of sintering. Some grain boundaries also demonstrate structuring within the plane of the boundary. The grain boundary shown in this slide, from a conventionally sintered specimen, shows ordered regions of oscillating high and low concentration of aluminium. An ROI was extracted around the width of the boundary and rotated head-on to view the evident structuring. The concentration profiles on the right side of the slide demonstrate that while oxygen concentration shows little correlation with the aluminium concentration, zirconium depletion and yttrium enrichment correlates with the aluminium enrichment. Only a few of these boundaries have been found in the datasets analyzed, and once again no connection with sintering type has become evident. These regions of oscillating segregation could be the result of structural anisotropy, such as grain boundary dislocations. However, this structural information is not discernible from the collected APT data. The triple points present in the analyzed datasets have also demonstrated significant variance. The triple points in all the specimens analyzed demonstrate silicon segregation levels higher than that both within the grains and at grain boundaries. The atoms with triple points were therefore isolated using silicon isoconcentration surfaces. Volume renderings of the concentration of these segregating species, aluminium, silicon, and yttrium, can be seen in the heat maps. The triple point at the top of the slide, coming from a flash-sintered anode specimen, demonstrates a homogeneous distribution of segregating elements. The triple point at the bottom of the slide, coming from a conventionally sintered specimen, demonstrates regions of relatively higher and lower silicon segregation, while the segregation of the other 2 impurities is relatively homogeneous. Once again, due to limited sampling, no relationship between triple point nature and sintering can be drawn. In conclusion, atom probe tomography has been successfully applied to both conventionally sintered and flash-sintered yttrium stabilized zirconia samples. Grain boundaries have shown variation in chemical segregation and uniformity, however no clear relationship can be discerned between flash-sintered and conventionally sintered specimens. Finally, triple points show both chemical uniformity and non-uniformity, however due to limited sampling, no relationship between sintering type can be drawn. Thank you.